Welcome back. We're getting to the point in the camp where we're starting to do more complex things than just simple one-line computations like changing the temperature from Fahrenheit to Celsius. And when you get into situations, which is normal, where you're doing more complex computations, you need to develop a plan for how you're going to do them. And that plan is called an algorithm. So this introduces the notion of an algorithm and a description of how we're going to write algorithms, and then we're going to use that as we start to go through the course examples, the camp examples, and go through the process of, okay, how do you program? First you plan out your design, and then you plan out what you're going to do in terms of computation. In other words, you write an algorithm, and then you start coding. So you don't just rush off and start typing. You do a little work ahead of time to make sure the typing will be beneficial. So what algorithms are, what they're not, and the writing style that we use, and how we're using these for programming. All right, so here's what an algorithm is. It's a step-by-step description of a process to perform a computation, or some people say a step-by-step description of a process to solve a problem. Algorithms have certain characteristics, and if these characteristics are not there, then you really don't have an algorithm on your hand. What you have is a good idea of a problem you want to solve, but you don't necessarily have the solution in hand. So number one, algorithms must be correct. They have to be correct, 100% correct. When we say correct, we mean 100% correct 100% of the time for all possible inputs, all possible values that we want to do the computation on. They have to be discrete, meaning each step clearly stops before the next one begins. Otherwise, we have this overlapping range of activities going on at the same time, and we really can't tell when the algorithm is stopping and starting or when each portion of the algorithm is stopping and starting. So we need to have a clear step-by-step description, and step-by-step means step number one ends before step number two begins, step number two ends before step number three begins, and so on. In order to make that happen, each step has to be really simple, like one tiny operation, one addition, one comparison. And each step has to be finite. You can't say, here's a step, oh, and by the way, it may take forever, because now we never can get on to the next step. We write these things in pseudocode. It's a little bit of English, a little bit of code. It doesn't really match any coding language, but it can be easily translated to any coding language. So the idea is you write these algorithms, you write these problem descriptions in a format that is not tied to any specific coding language, but anybody who wants to do programming can look up these algorithms and then convert them to the coding language that they're using at that point in time. We describe what the inputs and the outputs are, and we describe the steps. Again, those have to be those finite, simple steps taken to get to the output. And once this is written, any programmer can translate that code to their language. Now, there are hundreds of thousands of algorithms out there in the world that have been published by people. You can Google this stuff. And if you're looking for a particular, you're trying to solve a particular problem, my advice is don't try to solve it. Try to find an already published algorithm that solves it, and then you can code up that algorithm. People make their reputations by publishing really cool algorithms for things. Okay, so here's an example, find max. The idea is you're given a list of numbers. So our input is someone gave us a list of numbers, and they're in random order. And the output, the goal, is to find the maximum value. So we're given one list of integers. We're going to return a single integer, the maximum one. Now this L bracket n notation, that's shorthand for a list of n integers. So if n is equal to 1,000, then that would be L bracket 1,000. And the way you look at any individual integer is to just put a number in there. Like L5 would be the 5th integer. L20 would be the 20th integer. So stop for a minute and think how you would do this, how you would do this. If I gave you a bag of numbers, right, a bag of tiles, and each tile had a number on it, and I'm asking you to tell me which is the biggest number in the bag, well, the fact that they're in a bag, they're not in any order, right? So what would you do? Wouldn't you just reach into the bag, pull out the first tile, and say, okay, that's the biggest that I know of so far. So as far as I know, that's my maximum value so far. And then you pull out the next number. If that number is bigger than the one that you have already, you get rid of the original one and you keep track of the biggest you have so far. And then you pull out the third tile and you do that again. You're always comparing against what you think is the maximum so far. You pull out the fourth one, compare it again. If the fourth one is bigger than the one you have already for your max, then you get rid of that old max and now the fourth one becomes the new max. If it's smaller, you don't do anything, you just throw the fourth one away. So that's what's happening here. We're going to assume that the first number in the list is the maximum value. That's just an assumption. And then, for the rest of these numbers, we're going to do a little comparison. If the ith number is bigger than our current maximum, then the maximum is equal to the L sub I. Now, what's this for I equal 2 to n do? That's algorithmic form for how you do repetition, for how you can repeat sections of code. And we say for I equals some value to some other value. And the idea is that means we're going to do I equals 2, I equals 3, I equals 4, I equals 5, I equals 6, all the way up to I equals n. So if n was equal to 100, it would do 2 through 100. Do the following. And then down here, end 4, that's when we're done repeating. And inside there, all we do is we take the ith value, right, L sub I, or L index I, some people say. That's the ith number in the list. We're going to compare it against the current max. So when we first start out, remember max was equal to L1, and now we come through and now we're going to say if L2 is greater than max, if that's true, then now the max is equal to L2. Then we come back around the loop. We do for I equal to 3. If L3 is greater than max, then max is equal to L3. And we come around the loop again. Now I is equal to 4. If L4 is greater than max, then max is equal to L4. If L4 is not greater than max, we don't do anything. We keep the current max. So basically what we're always doing is we're keeping track of the biggest number we've found so far. And by the time we check all the numbers, we'll have the absolute biggest number. So when we're done with this, where we check all the numbers, we just return the maximum value. So remember, we said the input was a list of integers, and the output was a single integer max, and that's what this return max means. Return meaning, okay, I'm going to give you the answer back now. So this is a standard way to write an algorithm. It looks a little bit like code, but it doesn't really look like any particular coding language. But this is easily converted into, heck, almost any language you can think of. Another example, we're going to search. Now we're given a list of numbers, and we're giving a number to look for called the key. So our list of numbers is ln, and the number we're looking for is called the key, and we're going to return true if the key is in the list, and false if key is not in the list. So remember, true, false, those are Boolean values. So our output is going to be a Boolean value. Let's call it result. And there's a cheap trick here. Initially, we just assume that the key is not in the list. So right off the bat, we're saying false. In other words, we haven't found it yet. So for all we know, it's not in there. Let's just set result equal to false. And then we have this same kind of a little format where we do a loop. for I equal 1 to n do. Now what does that mean again? It means that we're going to check every number. We're going to check when I equals 1, we're checking the first number. When I equals 2, we're checking the second number. When I equals 3, we're checking the third number. On and on and on. So we're going to check all the numbers, and we're going to see if any one of them matches the key that we're looking for. Inside we have a little if then else. If, remember we did this yesterday checking for negative values, right? If L sub I is equal to the max, oh, max, that's no good, that should be key. Let me fix that. Cut and paste, strikes again. Okay, so if L sub I is equal to the key, then we found it. So the key must be in the list. Therefore, the result will now be true. And even though we found it, we're going to keep looking. It doesn't hurt to keep looking. It's computer doing work, not people, right? If you found it, you would stop. But it's not that important to stop. For this simple example, we can let the computer keep running even though the answer is going to be true. And then at the end we return result. So think about what happens if the key was not in the list. Let's say the numbers were between 0 and 100 and the key was 5,000. Then we start out with result equals false. This line here, Li equal asking the question if Li is equal to the key is always going to be false. Therefore, we will never execute this line that says result equals true, and the result remains false throughout the entire computation. But if the value is 0 through 100 and the number we're looking for is 5, eventually one of these members of the list would equal 5, and then result would equal true, and you'd return the result of true. So these are some basic examples of algorithms. What we're going to start to do is start to think through, for the examples we're going to do today, think through before we start coding, how do you go about solving this problem? And quite frankly, we're going to reuse these algorithms too.